All right, how's it going, people? Welcome to a very special edition of The Office Hour with Dr. Alberto Cruz. I am your host, Dr. Alberto Cruz. Today's video is something I'd like to call, Dude, Where's My Return Address? The purpose of this video is to expand on what we recently learned with the branch and link and the ret operation in ARM v8. I will demonstrate how, with non-leaf subroutine calls, that the return address is not preserved, causing some issues with how you believe a function should always return from a function call, particularly when it is a nested function call, one and the other, hence why we call it a non-leaf. All right, let me draw a example main function to illustrate the scenario that I'm talking about. All right, so we have three functions. We have a main, and all it does is call foo. We have another function called foo, which should be called by main. All it does is call bar. All right, now these functions don't actually do anything that makes sense logically. It's just for the sake of example. All right, inside foo, we have a call to bar. So that brings us over here to a definition of a function called bar. And all bar does is it returns 0. So what should happen here as we execute the program? Well, if you're looking here, main, we'll call foo, right? That much makes sense. Foo executes, then we have bar. What does bar do? Bar will run. All right, so the control of flow will go into the bar function. When we hit the return, we have this expectation that the return will place the flow back to where the function call was made. So it should call bar and it should return from bar back to this point, and then we hit the return inside of the foo block. And what will happen there is it should return back to main. All right. In terms of what we call these things, we refer to this function call as a leaf because it calls no other functions. These two things are referred to as a non-leaf function call. All right, so this is our expectation at the C level, and because this is an assembly class, we have to have discussions about how we can potentially ensure that that behavior is consistent when we code up our functions at the assembly level. So give me a second here. I'm going to code up some assembly ARM v8, which is roughly equivalent to this, at least with the context of what we're aware of. The two functions that you want to remember here are BL, right? The first one being BL. What that does is it unconditionally branches to any label you want, and it will place the return address in the register X30, as well as the function ret, R-E-T, which will return to the address contained in the register X30. All right, so let's code that up. All right, so this is what we got. We have a main, we have a foo, and we have a bar. All right, so if we're looking at main, we start off our code with just a branch and link instruction into foo. Note that the label and the instruction have the same instruction address. Because a label is not an instruction on its own, technically it is just indicating that instruction 0 is the start of main, okay? So main, the only thing it does is it branches into foo. So what we should expect here is the control to shift to foo. So at this point, the program counter will shift to a value of 20, and the return address, or X30, will be set to, let's think about that. So the branch and link operation will set the register X30 to the return point, where after the callee is done with its code, it should return. Where it should return is actually the next instruction after the branch and link. So that would be PC plus 4, but PC plus 4 in the context of when the call was made, which would mean 4, right? Think about that. When we call foo, we let foo do its thing. When foo is done, it'll return to 4, okay? Not 0, because if you set the return address to 0, it's going to get stuck in an infinite loop where we'll keep calling BL foo, okay? So that means that this instruction address 4 is our current return address, all right? All right, let's just take a second to think about this here. So that means that when we jump into foo, whatever it is that we end up doing seems to make sense, because when you're done with this instruction, BL bar, and you get down to RET, it will look into X30 to determine where it should jump, and that happens to be instruction address 4, which would be here, which would appear, at least in the context of the depth of these two calls here, that it would be able to get back to main, all right? But what happens? If you look over here, foo executes BL bar. What does that mean? So the branch and link will set the current PC to that target, and it will overwrite the contents of X30 with PC plus 4. So what happens is when this call is made, it will indeed set the PC to 0x80, okay, and perhaps that makes sense, but whatever was previously in X30 will be overwritten with the current PC plus 4, which would be 20 and 24, all right? So that's the main issue at play here, is there's only one return address. So if you're just focusing on the depth of this call, bar being called by foo, what happens? The PC will jump to that address, bar, right? Remember that the label is not an instruction itself. It is just a label. The actual instruction located at 80 is to ret. Ret will return to whatever the address is located in the program in this X30 register. It'll set the PC to that value. So that means it will return to X24, because that's what the current contents are of X30. So that would mean it would return to this thing. Now that made sense. That actually allowed foo to call bar and for bar to return back into foo. But that's not the entire example here. The idea was main calls foo, foo calls bar, therefore foo should return to main. However, if I hit this return address, what is contained in X30? Okay, so basically if I hit this return, it must set the PC to the contents of X30, which are address 24. So essentially what happened was this second branch and link ended up destroying the point where we would return into main, all right? And that's actually the point of this example, is to explain why non-leaf subroutine calls will clobber the return address, and it'll motivate our discussion for something called the stack. Essentially what we're going to do in the following videos, we're going to discuss what the stack is and describe how we can use the stack to store local variables such as the return address, which would potentially solve this particular issue. All right? Have a great day, everybody.